Okay. Hello, everybody. This is Maisie. I'm going to be doing a walkthrough of quiz number 4. Um, so let's just jump right in with the first problem. So our first problem here is a resonance problem. It tells you to draw all of the valid resonance structures that contain no more than 2 atoms with formal charges and circle the ones that are contributing. So this question specifies that it wants you to draw all resonance structures and then go back and decide which ones are contributing. So that's an important piece of information. So this is our starting material. We have this thing with a nitrogen on one side and a boron on the other side. Remember that our goals in resonance, right, is to, number one, complete as many octets as possible. So complete octets. And we want to give electrons lots of space. So the reason why resonance is so great, right, is why electrons like to be in resonance is because it gives them more space to run around. They don't have to be squished and confined onto one molecule or one atom. So let's highlight, first things first, a source of electron density in this structure and a source of electron deficit. So right here, we have a lone pair on a nitrogen, which based on some of our other resonance practice, right, we should recognize as a source of electrons, a source of electron density, so that that lone pair can get donated to participate in a resonance system. And then on the other end of the spectrum, we have a boron right here. And this boron is electron deficient. As you can see here, boron without a formal charge means that it has an incomplete octet. This boron only has 6 electrons. So this is an incomplete octet. And this is an electron source, which are good places to start in a resonance problem. Now, one thing to note, right, when we're going back to determine which of these structures we're about to draw are contributing or not, if there is some way that we can complete this boron's octet, if there's one resonance structure or 2 or 3 where that boron has a complete octet and everything else also has a complete octet, then those are going to be the contributing resonance structures. So contributing resonance structures have the maximum amount of possible octets full. So if you can fill it in one but not fill it in another, then the one that you can't fill it means it's not contributing. So that's important. But we'll come back to that when we go to compare our contributing resonance structures at the end. So I know this problem says don't use arrow pushing, electron arrow pushing. I think it's almost impossible to explain a resonance problem without using that. So even though your final answers won't have those arrows in them, mine will, so just for your reference. So in a resonance problem, we should always start with a place of electron density, right? So a place of electron density that we already sort of identified in this problem is that nitrogen. So let's just push that lone pair and see how far we can go with this. So first things first, we push that lone pair, and now we can push this bond up onto here to make sure that that carbon doesn't have 5 bonds. So let's draw that structure. So this next structure looks like this. So we have a lone pair on this carbon, a double bond here, and a positive charge on that nitrogen because we've given it 4 bonds instead of 3. Let's keep going. Well, now that lone pair is still a source of density, so let's push it again. We can push that down here, and we can push that negative charge onto this carbon right here. So let's give that a try. So now that negative charge is on the bottom carbon of the ring, opposite the nitrogen. Let's keep pushing. Let's push this here to make a double bond. And now we're going to get to something very important, because what have we just done? Well, we've just completed boron's octet, right? We've just given boron, even though we've given it a formal charge, which it doesn't necessarily love, but it is definitely happier with a formal charge than it is with without a complete octet. So we've given it a complete octet, which makes it very, very happy. So now you can keep pushing these electrons around, and you could take this electron pair right here. Oops, sorry. You could take this electron pair right here and push it up onto this bond and push this bond over here, and then push this bond back onto the nitrogen. But when you do that, when you break this bond right here, you are uncompleting, if that makes sense, boron's octet. And so that is everything you do from this point forward is going to result in an incomplete octet on boron, and therefore is not going to end up being a contributing resonance structure. But because this problem asks you to write out all resonance structures, not just the contributing ones, we will push the arrows to show the other possibilities here, even if they won't end up being contributing. So let's just do that now. So the next contributing resonance structure would just be identical to this one right here, because all we do is push these electrons back onto this carbon right here. So we don't need to draw that one twice. And then from this structure, if we just duplicate this structure here, we end up with, we can push electrons here, and then, oops, that's going the same direction that I went already. So we can push electron density here, and then push this up onto the carbon to create a new structure that looks like this. I keep forgetting to switch colors. So we could have this, and then the last possible resonance structure will end up being something that just actually has all of the pi bonds in the benzene rotated around, because we have sort of come full circle here. So you can see that once I do this arrow pushing, so we're going to push this lone pair over here, and then donate electrons back onto the nitrogen to relieve that positive formal charge. So this is no longer positive, and now we've resulted in a simple rotation of these bonds. These guys just all shifted to be in the opposite position, which is a resonance structure that you might have just thought of, but it's nice to see that we can sort of get to it through just doing it step by step, arrow pushing wise. So these are all of the resonance structures for this compound. And what I'm going to do is now I'm going to erase the arrows, because it says don't show electron pushing arrows, so that we can compare these resonance structures. So these are your resonance structures. We have 1, 2, 3, 4, 5, 6, 7, except 2 of them are the same. So we have 6 unique resonance structures here. So these are our 6 unique resonance structures because these 2 are the same. However, there's not going to be a lot of these that are contributing. And this is sort of what I tried to hint at before, is that we have this boron that is practically, actually not practically, literally the only structure that has that boron with a complete octet, and therefore this entire structure has 0 incomplete octets. So 0 incomplete octets. The only structure that has 0 incomplete octets is this guy. And so therefore, there's actually only one of these structures that's contributing, instead of having all of these resonance structures be contributing, because this is the only one that has all of the maximum amount of complete octets full. So that is question 1. Question 1 is pretty complicated, so that one took a little while. But let's move on to question 2. So question 2 is going to ask you to draw the 3 staggered conformations of 1,2-dichloro-2-methylpropane. It sounds like a daunting name, but you guys are naming masters at this point. So this is 1,2-dichloro-2-methylpropane. So first of all, we got a propane, so that's 3 carbons. dichloro, so it has a chlorine on carbon 1 and on carbon 2, and then 2-methylpropane. So that means there's also a methyl on carbon 2. So this is your structure. Now we're going to 3D it a little. So let's just make it 3D. We will give it a staggered conformation to start, which means that this trans structure is a good way to start your backbone with the Cl, and then your wedges and dashes are going to be on the top and the bottom. So over here, both the wedge and the dash are going to be hydrogens, and right here, one of them will be a chlorine and one of them will be a methyl. It doesn't matter which way you do it, because this is not a chiral center, because you have one methyl and you have another methyl, right? So it's an important distinction. But now we've 3D-ified this thing a little bit. So let's get to work translating this into a Newman projection. And we'll just translate this one first into a Newman projection. And then we can do our rotations. So this is our Newman projection. I'm calling this carbon 1, this carbon 2, this carbon 3. So we got carbon 1 in the front. I'm going to highlight it. So this is carbon 1 and this is carbon 1. And then in another color, I'll highlight the back. So the pink is the back carbon, and that is this guy back here. So this is carbon 2. So carbon 1 is purple highlight, and carbon 2 is the pink highlight. So now let's just start throwing things onto this Newman projection, right? I forgot to finish setting it up. There we go. So let's just start throwing things onto this Newman projection. Well, this first carbon, if we were to take this structure, right, now it's flat in the plane of the page, we're just going to sort of pull it up out of the page so that your eyeball is right here. So you are looking straight down the 1,2 bond, which is this bond right here. So if you're looking straight on like that, the thing that's on the top, right, is that chlorine. So let's put that on the top. We have a chlorine right here. That is the chlorine that's on top there, and I'm going to highlight it in pink. And then the other two things that are on the bottom, down here and down here, are hydrogens. So it doesn't matter which side we put them on. But just to be specific, right, if your eye is right here and you pull this whole thing to look at you, the wedges are going to be on the left and the dashes are going to be on the right. And this is a really tricky concept to do without using your model kit. So I highly recommend you try and do this one with your model kit. So we're going to call the one on the left H1 and the one on the right H2. So this would be H1 and this would be H2. And then all we have to do is think about this back carbon exactly the same way. What is the thing that's down on the back carbon? We have a methyl that's down, right? This methyl right here is down. And then we have another methyl and a chlorine. So now we have to decide which one's on the left and which one's on the right, just like we did with the hydrogens. Well, the wedges and the dashes are going to be the same thing on the back carbon. So the wedges are on the left and the dashes are on the right. And you can, again, practice doing that with your model kit if you don't believe me, because it's very, very useful to see this in real life. So on the left, same side as the hydrogen, you can see, same side wedged, same side wedged. We're going to put the chlorine that's on the back carbon right here. And then we're going to put the methyl that's on the back carbon right here. And that is your first Newman projection. And now everything gets a lot easier, because going from the sawhorse to the Newman projection is the most complicated part. And then all you have to do is pick one carbon and turn it like a doorknob a bunch of times. So to do that, this is what you're going to do. I usually do the back carbon as the one that I rotate like a doorknob. Don't ask me why, I just always do it that way. You can do the front if you want, but I'm going to show the back myself. So I'm just going to relabel this because I'm not changing what's happening on the front carbon at all. I'm just leaving what's happening on the front carbon alone. And then what we're going to do is just turn everything clockwise by about 120 degrees. So let's do that. if I turn this whole thing 120 degrees, each one of these substituents will take a place of another one, right? So the chlorine is going to end up where the methyl is. The methyl will end up where the other methyl is. And the unlabeled methyl or the unboxed methyl will be where the chlorine was. And then all you have to do is do that exact same thing one more time. So we're going to take the chlorine and put it where that methyl was, this methyl and put it where the unboxed methyl is, and move the methyl to where the chlorine was. So this is the unboxed methyl, this is the chlorine, and this is the boxed methyl. And that is all you have to do to draw all of the staggered conformers. Now, keep in mind, there are also eclipsed conformers that happen. There are also eclipsed conformers in between each one of these staggered conformers, but the problem only asks you for your staggered conformers. So now it also asks you to circle the conformation with the highest energy. So highest energy basically means most strain or most interaction between big groups. So we really want to try and separate big groups as much as possible. So the things that are big and chunky on this molecule, right, are the methyls. The methyls are kind of in the way, and then the chlorines are also in the way. So you want to find the best way possible to separate the methyls and the chlorines from each other. So this chlorine, we really want to be as far as possible from the other chlorine in this particular example, because the chlorine-chlorine interaction is going to be really big. So if we try and find the one where the chlorines are the furthest apart, this one, they're pretty close together. This one, they're pretty close together. And so this one is the one with chlorine the farthest apart. And so this one is going to be your, excuse me, your lowest energy conformer. And then we will find the highest energy conformer. So the highest energy conformer is going to be the one with the most interaction between the chlorine on the front carbon and the chlorine on the back carbon. And so both of these actually have equivalent interaction between the two carbons. So these two are between the substituents on the two carbons. So I was also worried that I was going crazy when I said this about the chlorine being more lower energy if it's farther apart. I just double checked Morton's answer key, and it looks like he believes that he chose a dumb compound to ask this question about. So I wouldn't worry too much about the conformation with the highest or lowest energy, because it's a little vague in this case. So let's move on. Let's do the last part. So we'll talk about the last question down here. Okay, let's talk about question 3. So question 3 is another Newman projection question that has to do with chairs. So very important. Chairs will, you will be sick and tired of chairs by the end of this class. But not yet, maybe, not yet. So this question, all it does is ask you to draw both chair conformations of cis cyclohexane 1,3-diol, and then draw the Newman projections associated with those. So I'm just going to draw both of our chair outlines here. So this is one, and this is the other one, and this is your other chair. And then he already has pre-labeled the carbons that he wants you to use. So this is going to be carbon 1, and this is going to be carbon 2. This one, or sorry, carbon 3. And this one is carbon 1, and this one is carbon 3. So now what we have to do is we have to talk about substituting these chairs, and then we can do the Newman projections afterwards. So let's just do the substitutions, right? There are going to be 2 different chairs of this conformer, or 2 different chairs of this compound. And they specify that this is a cis diol, which means that both alcohols are on the same side of the ring. So they're either both going to be up or they're both going to be down. It's totally up to you which one you pick. You can make them both up, you can make them both down. Both of them would be correct. So let's just draw them. I'm going to draw them up just because I think that's easier. A little trick for deciding whether they should be drawn axial or equatorial. An up carbon, so a carbon that if you were to draw an arrow on its corner, just like I did, an up carbon means that the axial position is up. So this is the up chlorine, or sorry, is it chlorine? Yeah. Sorry, it's alcohols. The alcohol would be in the axial position if we were deciding to do it up. And the same thing here, this is an up carbon because it looks like an arrow pointing upwards. And the alcohol is also up. And you will notice that they are both up, which means they are cis to one another, which is exactly what the problem asked. And now you're going to notice that the things that were up carbons on the first chair are now down carbons in the second chair. So you can do the same exact trick, right? This arrow looks like it's pointing down. This arrow looks like it's pointing down. So they're both down carbons. On down carbons, the down position is axial, but that means the up position is equatorial. So substituents that are up stay up in both conformers, and substituents that are down stay down in both conformers. So since they're both up, and since these are down carbons, they are both going to be in the equatorial position, because on a down carbon, the equatorial position is up. So this is going to be an equatorial OH that's going up, and this one is also going to be an equatorial OH that's going up. And you can still see that they're both still up, even though we did the chair flip. So this is what your two structures will look like. So now we can walk through making them into Newman projections. So let's draw the Newman projection here. So this is an up carbon, so this is going to look like this. Let me just draw this out real quick. And then our other Newman will look like this, because we've done the flip. And I will show you a trick to look at that as well. So another trick is that, remember, we know that this one, when I say up carbon, that means this carbon is one of the pointy uppy ones in the chair. So they label this as carbon 1 and this is carbon 3. This is also an uppy carbon, just like that. And 3 is up, like we talked about before. And you can confirm that here. And so what is directly up on carbons 1 and 3? Just the OHs, right? And everything else is H's. There are no other substituents on this molecule, so you can just put H's in all of the other spots. And now we can do the exact same thing over here, right? Because now 1 and 3 have both become down carbons. So now that they're both down carbons, just like with those arrows that I showed, right? These are down. So that means the whole carbon is down. The up position, right? This would be the down position on a down carbon. That's axial. So the up position is going to be equatorial. It's going to be off to the side like this. And you can still see that they're on the same side, the same face. They're both above the center plane of, they're both like above this line, right? And everything else is a hydrogen. And so those are your two Newman projections. And now it says circle the chair corresponding to the lower energy conformer. We should know by this point that the lower energy chair conformer is where the big substituents are equatorial, right, where they're off to the side as much as possible. So this guy is going to be our lower energy chair conformer. That's it for quiz 4. I will be putting up more videos, quiz 5 through whatever we get to this week. yeah, if you have any more questions or if you point out anything that I did wrong, it's definitely my fault. This is Maisie. So just shoot me an email and I will attempt to fix it. Have a good day.